So the question is, could really come like straightforward. Do we really need to put all the data into Bookkeeper? Can we be smart and creative that we are able to kind of push the 90% of the data into a much cheaper storage layer? And that was the reason why we introduced Pulsar tier storage, is to lower the entire cost of their storage bill. So we introduced tier storage back in 2018. That was released in Pulsar 2.2. With the introduction of the Pulsar tier storage, it actually introduced another tier of the storage there, which means 1% of your data is the hot data that can be cached in the broker for low latency streaming. 9% of data are warm data that will be stored in Bookkeeper with replication for availabilities. Those data will eventually be tiered into tier storage, and 90% of the data can be offloaded into a cold storage, and that would be tiered and stored in a much cheaper storage options, and that's the creation of tier storage. And it's very easy for Pulsar to do that. Is if people know about the design details of Pulsar storage model, you understand Pulsar storage model is a segmented stream model, meaning each time when they roll over a segment, they will see a current segment and writing a new segment, and this segment will be stored in Bookkeeper and distributed across different storage nodes. So with this model, it's very easy to implement a model on tier storage. We can easily just move a sealed segment to tier storage, and that's how we implement the first version of the tier storage. And eventually, when we introducing like tier storage into Pulsar, Pulsar became one of the pioneers of introducing this tier storage concept. We're almost the first one introducing the concept back in 2018 for Pulsar 2.2 release. And Confluent essentially follow us, copy the feature as a preview in Confluent platform back in January 2020. And Red Panda also do similar thing called shadow indexing, essentially is a version of tier storage back in December 2021. And Kafka community recently released 3.6, including an early access version of tier storage. I think majorly contributed by Uber, and kudos to Uber's contribution to the broader Kafka ecosystem. But coming back to tier storage is one of the most demanding features that has been adopted by like Pulsar adopters. I just want to show some of the real production use cases about how tier storage has been using in production. This is a screenshot from one of the users of Pulsar. It actually offloads data in 3 gigabytes per second. So tons of the data going through Pulsar and being offloaded into tier storage. And because a lot of the data has been eventually moving from Bookkeeper to tier storage, it significantly reduced the cost of storage, improved the entire stability of the business operation. So it doesn't really need to rely on Bookkeeper itself, but it can rely on much cheaper options like S3. Even you are running on-prem, you can use HDFS for that purpose. Essentially, also kind of present the possibility for Pulsar became a storage for infinity streams. But there's certain challenges in the implementation. I mean, that's the limitations that I highlight for the current implementation. Most of the limitation also apply to the other tier storage implementation in the broader data streaming ecosystem. The first one is the Pulsar implementation is offloaded the data based on segments. So it only offloads data when the segment is sealed. So it doesn't support streaming offload. So that from time the data arrive in the broker towards the data appears in the tier storage, it might take long duration. Data is also stored in almost like Pulsar's own format. A lot of tier storage implementation also store in their own format. So that has a certain limitation, is that if I offload data into tier storage, that means only that data streaming system can use that format. There's no other system can like really leverage the data being offloaded into tier storage. And if I need to integrating with the Lakehouse system, it requires additional efforts to integrate that. For example, as what Mathieu mentioned in his keynote, you might use a connector. Sometimes you might use a Flink job to read data from Pulsar and writing to Iceberg or Hudi or Detla Lake. And because the implementation is usually stored data in its own format, that means it requires a lot of efforts to tune the read performance in order to serve the purpose of reading back the data from tier storage. And the last thing is the most important missing pieces is that there's no schema version, schema information as part of the offloaded data. So that means if you want to use the data offloaded in tier storage, there's no way. You have to kind of couple it together with a Pulsar schema registry or Kafka schema registry, depending on which one you're using. So with this limitation is what we have been thinking about beyond using object store as a tier storage. What is the ideal tier storage that we should have? After talking to a bunch of the users in the community, talking to our customers, we kind of summarized that the needs of an ideal tier storage, first is that it has to, including the schema information, the storage itself would also have the schema enforcement and governance. So in that way, you can ensure the data integrity of the data offloaded in tier storage. It should also have the robust governance and auditing mechanism. The storage format should be open. Open meaning you can use external processing engine, query engine to process the data without talking to the data streaming system. And lastly, it has to further reduce the cost of your storage. So cost efficient, how you can save reduce the amount of data stored in the tier storage, how you can save the data transfer between your tier storage and your application. And so that, to summarize this, is we find does this ideal tier storage even exist? And the answer is yes. People already hear about that, talking about Data Lake, Lakehouse. And Lakehouse is such a system that meets the requirements that we're looking for. Is it offers, in the Lakehouse ecosystem, like most popular one are Hudi, Iceberg, Detla Lake. They are built based on Apache. All these are open standard, so you can use a lot of query engines to query the data that's stored in those formats directly. So you don't need to go through broker, any other kind of a data streaming system in order to interpret the data offloaded into tier storage. And it's also, the low storage format has been already developed for years. There's tons of the performance enhancement is already building into those formats. So you don't need to spend a lot of time to really tune the performance there because they already proved in production, proved by so many different industries there. So that's how we get started the journey on kind of thinking about, can we use Lakehouse as a tier storage layer for Pulsar? And we made it, and we built Lakehouse tier storage. Essentially, like before Lakehouse tier storage is introduced, there's only one way you can write data into Lakehouse from Pulsar. Essentially, is using a connector. That connector can be a Pulsar IO connector reading data from Pulsar and writing to Lakehouse, or maybe using Flink to read data from Pulsar and writing to Iceberg or Hudi. But the problem of that approach is that you're still operating on two different systems with two different schemas, one sitting in your data streaming system, one sitting in your data lakehouse system. And there's kind of conflicts or inconsistency in regards to the data schema across different systems. A more natural way is that if we make Lakehouse become the tier storage there, then we can offload data directly into Lakehouse in a streaming way. And if the data is already stored in Lakehouse, then we are able to kind of reading back in a streaming fashion. And so you can continue using Pulsar's API, Kafka's API to replay the data in Lakehouse. Or if you want to bypass the data streaming layer, you can just use your query engine or data process agent to process the data directly in the Lakehouse. And the topic, the lifecycle of the data can either be managed by Pulsar or can be managed externally by the Lakehouse system. And Pulsar then can become an infinity storage with very efficient storage format, and that can be used for people to keeping data as long as they want. And that eventually became what we call a streaming Lakehouse concept here. Essentially is an extension of a data streaming system using Lakehouse as a storage layer. And this paradigm can expose two APIs. One is the streaming API, allow people to streaming writes or reads the data in and out of the streaming system. You can use Pulsar API, you can use Kafka API. It doesn't prevent you from doing that. It also provides the ability for people to bypass the API, streaming API to read the data directly from the Lakehouse, which is the table API. And this approach is supports existing applications very well, so you don't need to change your application. But it also not just saving the cost, reducing the entire cost that you're spending on tier storage, but as well as unlock a potential for the query engines to leverage the information stored in Pulsar and Lakehouse to do unified batching streaming, which is an example that later Ingjun is going to demonstrate using Rising Wave. The entire implementation is done through a Lakehouse offloader. And what the offloader essentially is that it can be run as part of a broker. So when broker receives the data, it can streaming the data directly to the Lakehouse and seal the data when the broker roll over to the next ledger. It can also be run as a separate services. If you're running on Kubernetes, you can move the entire offloading services as a separate services so it doesn't impact the online applications. The data offloaded into the tier storage can be read back by the broker in a streaming mode, or it can be read directly using the Lakehouse API, so you don't need to go through the broker again. Because if you need to, that broker read the data back from tier storage, it requires tons of the network that you need to spend and kind of pay to the cloud providers. So just with offloading data into tier storage, you can leverage the schema information to further compact your data from a row-based format into a columnar format. And this is just a simple example. If you just kind of produce the data in Avro format and writing into Lakehouse, you can result in kind of 5-time storage cost reduction. And this is just a simple test. It doesn't represent all the different kind of workloads. It really depends on how well the columnar compression can apply to your schema. And you probably can get more like storage cost reduction from Lakehouse tier storage. Lastly, I want to share right now the implementation is available across all the 3 popular Lakehouse solutions, including Detla Lake, Iceberg, and Hudi. There's only one problem with Hudi is it doesn't support streaming reads, and that is a limitation from Hudi's Java API. We have been kind of working with the Hudi community, trying to figure out what is the best approach to allow us to be able to streaming read the data back from Hudi format. And then this is kind of an overview in terms of kind of what we have done with Lakehouse tier storage, but I want to use this opportunity to kind of do a quick demo. I hope I can run a demo within a couple of minutes. But this, I want to kind of really use this opportunity to kind of show kind of end-to-end is I will use Detla Lake, but I do also have Hudi and Iceberg demo. If people want to kind of check that, you can talk me after the talk. So the demo would be I would use a Kafka producer to produce the data into a Pulsar cluster. So that is demonstration of Kafka Pulsar supporting Kafka protocol. And then we offload the data into a Pulsar topic, offload the Pulsar topic into Detla Lake. And then we demonstrate using Spark SQL and AWS Athena to read the data from Detla Lake. And lastly, we will consume the data from Delta Lake, from the topic that is already offloaded into Delta Lake by using Pulsar consumer and as well as the Kafka consumer. And I did a lot, but hopefully I can finish that in a couple minutes. So let me see. I need to, okay. Hopefully the network works. So that is a demo. Essentially, we're going to, that is showing that we are repeating the steps that we're going to demonstrate. Writing using Kafka protocol, offload the Pulsar to Delta Lake, and query the data in Delta Lake, and consume the data using Pulsar consumer and Kafka consumer. So let's see. So all the test is done on kind of a stream-native cloud cluster. We'll get started by, let's see. Okay. We will first by creating a topic. We're going to create a topic called delta-klp-topic-I. And one second, let me just double check it's playing speed, twice speed. So then we'll start a producer. The producer is a normal Kafka producer. So you can, if you already have Kafka application, you can just use your Kafka application. It will just produce using a Kafka schema registry. And so we will write all the records using Avro format. We are sending 800,000 messages. And it created kind of 8 producer. Each producer produced 100,000 messages to this topic. So it's running, as you can quickly complete. And that's the schema of the data we return into the topic. So after the data has been written into the topic, we go back, check the topic stats. You'll find the topic stats show the broker already received 800,000 topics. And there's 2 ledgers has been created because of the data producing into the topic. And you also can find there's a cursor called offloaded is already created. And that offloaded cursor is actually a tier storage cursor. Is reading the data, receiving the data from the topic and offload it to Delta Lake. And that's how we check the Delta Lake. You'll find there's a table is being created in AWS S3 that is including kind of 2 Parquet files, and that is the data being offloaded from Pulsar to Delta Lake. And now I think the offload is already complete. You will see the data is already kind of fully consumed. And then we'll go back into using Spark SQL and Athena to kind of query the data directly out of the Delta Lake. So that's the Spark SQL. We're going to load the table from Spark SQL, and we're going to run the count. It will quickly return 800,000 records. So that is the data being offloaded into Delta Lake. You can also selecting the records coming out from the offload table. This is the schema. You can see all these fields that is coming from Pulsar schema that would be mapped into Delta Lake table schema. And obviously, it also ingests certain properties that including Pulsar informations. Lastly, this is kind of a couple rows that are being selected out of the table, so you can see all the properties of fields that are coming out of that. So with that, we switch to Athena. Athena is managed, I think, Presto offering provided by AWS. You can also load the offloaded topic as a table, and then you can create a table pointing to the offloaded data. And then once the table is being created, you're able to run any queries over the Lakehouse table. So let's just do a count. It should return like 800 and 800,000 records there. So that's the kind of the batch query part. In addition, I'll probably just like fast forward is that we want to kind of show that it's able to kind of consume using the Pulsar consumers. So it's able to kind of creating subscription using the Pulsar consumer. But first step, we want to unload the topic so it doesn't read the data from the cache. It shows that we are reading the data from the broker. So this is a Pulsar consumer. So the Pulsar consumer, it's a normal Pulsar consumer. You can just consume as what you want, and I think it already ran. And the next one is the Kafka consumer. Is actually similarly is we're creating a Kafka consumer to read the data directly from the Pulsar topic. It's just because Pulsar is able to support Kafka protocol. But given the length of the talk, I'm going to just stop here. And if you are interested in more about the demos, I do also have other kind of demos with Iceberg and Hudi as well. So with that being said, is all these Lakehouse tier storage is not, it was started because we want to kind of reduce the cost, but we quickly identified that it just unlocked a new pattern is that you are able to really integrating with a query engine that is able to do both batch and stream processing. And with that, I'm going to hand over to Yingjun. He's going to walk us through the integration between Rising Wave and Pulsar.
All right, thanks for the time. Is it working? No. Okay. So yeah, I'm Yingjun, and I'm the founder and CEO of Rising Wave Labs. So one slide about what Rising Wave is. Rising Wave is a distributed SQL streaming database, and we open source the database in 2022 under Apache 2.0 license. And within a year, we have already gathered 5,000 GitHub stars, over 140 GitHub contributors across the world, and we have over 1,000 Slack community members, and the system has already been deployed over 100K times across the world using Kubernetes, not just Docker. It's Kubernetes deployment. So what is Rising Wave? And Pulsar is a great system, right? Well, and everyone knows that Pulsar is for messaging and for streaming. And if you have an application and it can generate a huge amount of data, then you can use the Pulsar to consume the data, right? It can help you to buffer or to cache the streaming data. The next question, once you have the Pulsar, the next question is that, okay, how you deal with this data, right? You probably need to have some stream processors to handle this data, to do some stream transformation, to do some analytics, right? So also we have a lot of great systems like Storm, Spec Streaming, Flink, Samza, and many others, right? And now we just give you everyone a new solution that is Rising Wave. So the next question is that, okay, people will wonder, okay, why we need Rising Wave, because we already have so many systems, right? Rising Wave is drastically different from these systems in that it's a streaming database. It's not just a stream processor, but a streaming database. It's a streaming processor plus a database. You can think of it in that way. So instead of just managing your, what a streaming database means, it does not just mean that, okay, it brings you the PostgreSQL-like experience for operating for processing your streaming data. It doesn't really mean that, merely mean that, okay, it can help you to, store your data and serve your ad hoc queries. It also means that, okay, it can actually manage your states, local states, or local stream processing computation states in the database, so that you can scale in and out the stream processors, streaming processing jobs elastically and at a runtime, at a system runtime, without stopping world. So Rising Wave's architecture is quite different from the conventional stream processors in that, okay, if you check on any of these stream processors in the market, you will find that, okay, they all adopt the so-called coupled compute and storage architecture, right? And that's great. But the tricky part in the cloud environment is that this kind of architecture may suffer from, some downtimes if you want to scale in and out, or probably if you want to just want to let's say change a schema, right? But in Rising Wave, it adopts the decoupled computing and storage architecture, meaning that the states are actually, and as well as the storage, are actually persisted in S3, and the local machine will basically to cache the cache the internal state so as to accelerate the query processing. And very similar to Pulsar, Rising Wave adopts a tiered storage for state management, meaning that the local state will, it's tiered, right? So it's asymmetry-like structure to manage your state in the cloud. So the great thing here, the way we found is that using such kind of technology, we achieved 10 to 100 times more cost efficient, especially when handling the complex queries like joins. Let's say that if you want to join multiple windows, right? Joining multiple data streams, and if you want to do big time window joins, it can be much more efficient than the conventional systems. So when we talk to customers, Rising Wave customers, they were used, we always can see this kind of their stacks look like this. It will be like, okay, they have the messaging system, probably Kafka, probably Pulsar, right? And then some of them have the batching Spark to do the batch ETL. And some of them use, the Rising Wave for doing the streaming ETL. And then dump the data into historical data into Data Lake, like Iceberg, Hudi, and Detla Lake, right? So it's kind of popular. This data stack is kind of popular, but when we talk to customers, then they will all still complain that they will say, okay, look, there are still data movement. I still need to synchronize across two different pods, right? I have the messaging queues, and I need to periodically move my data from one side to another side, right? And I probably need to use two sets of data systems. It's kind of complex, right, in terms of operating. And they also need to think about, okay, how I can deal with the, data consistency, right? Well, okay, probably I spend my last 7 days data in Pulsar, but I want to spend probably a years of data in Hudi, Iceberg, and Detla Lake. Then how do I handle the consistency? It's kind of complex. So last month, I just wrote a blog that, okay, why Kafka is the new Data Lake. I wrote it, and some people really like it, and some people said, okay, why we do that, right? So the biggest argument I made in this blog was that, okay, you actually don't really need to maintain too many systems. You can actually just treat your messaging systems as a data lake. It's a streaming data lake, right? So what it means? It means that essentially in a company, they can just store your data in the messaging system, in Kafka, in Pulsar, and in other messaging systems. And then the messaging system will deal with the data lake. So that you can use the stream processor, streaming database like Rising Wave, to directly only talk to the data lake, talk to the messaging systems. And you can also use your, let's say, the real-time analytics systems like Lakehouse, like Spark, like Trino to talk to the messaging systems. You don't need to deal with two types of systems, right? And if you only deal with one single system, then there's no consistent issues, right? Because these consistent issues will be dealt with inside of the Pulsar or Kafka, right? So essentially, we found that Pulsar is the first one to implement this idea, right? They, as GG just mentioned, they actually have already implemented this idea and have already pushed this into production, pushed a new architecture into production in some of their customers. So And what we found is that, okay, if once we after implementing this architecture, we found that, okay, what we achieved? We achieved actually 3 to 10 times better streaming ingestion performance compared to, comparing to previous architecture. And we also saw the 80% reduction in the storage size. And since you actually have already mentioned, okay, why we can achieve the 80% reduction in storage size, right? I'll talk about, okay, how we can be more performant in streaming ingestion. So in this part, well, okay, essentially the idea is kind of simple, right? In using the previous architecture, what we do is that, okay, what Rising Wave does is that, okay, it will directly talk to Pulsar. It will only talk to Pulsar interface or the broker interface and, okay, give me data and give me the data one by one so that, okay, I can read every single lines of every single event and then process them, right? That's an old method. But once we have the new architecture, the data lake integration, then everything changed. We can essentially, step one is that, okay, we can essentially read the historical data directly from the data lake, from the Iceberg and Hudi and the data lake. We can directly read the data, directly talk to a data lake by bypassing the broker interface. After reloading all the historical data, then we can talk to the broker and we can talk to Pulsar and say, okay, look, give me the most recent data. So that's why it can be much more efficient than the previous one because, well, it's in a data lake, the data format is basically a Parquet-like format, right? And Rising Wave has a vectorized engine, and we do not no longer need to deal with the data parsing, or probably no longer need to do, how to transform data. We can just load the data from there. Instead of processing the data one by one, we can process data in batches. And it gives us a huge speed up in terms of performance. Yeah, so in terms of implementation, we are actually, we worked with this project not just with the Pulsar community, but also with some other communities, for example, the Iceberg community. We are collaborating with the official Iceberg community, and we brought this project into Apache Foundation called Iceberg Rust, which means that, okay, if you have a Rust-based system, then you can use this system to directly talk to Iceberg without bypassing the Java interface. And it's under Apache Foundation, and many companies are pretty interested in this project. And in the future, we'll definitely be working collaborating with some other communities like Hudi and Detla Lake to further think about, okay, how we can push the streaming Lakehouse thing into a market. Yeah, that's my talk. Yeah.
Thanks, before I close the talk, I want to kind of use this opportunity to thanks to the team that have been working on this. Big shout out to Streamlit team, Hang, Yong, Yan. Both are the committers of Pulsar and Bookkeeper. You probably already see them across different community channels. They have been working really hard on getting these Lakehouse tier storage in production, and it is going to save tons of the users and customers money. Big shout out to kind of a Rising Wave team. They have been kind of working together with my team on how to integrating with Rising Wave together with Pulsar and demonstrate the idea how this Lakehouse tier storage can be beneficial to query engines. And lastly, I want to kind of share a couple future plans. Right now, this is tier storage. Lakehouse tier storage is in a private preview. And if you want to try it out, if you want to kind of work with us, feel free to reach out to me, like any Stream Native team members. And lastly, as I mentioned, we also kind of working with One House. They are also kind of the sponsor of the summit. Is they have a project called One Table. The idea is to providing one API for all the Lakehouse system. So we are going to integrate with One Table. So in that way, we don't need to do implementation with many different Lakehouse systems in the future. Lastly, I want to call a kind of program. We'd like to looking for more partnership, cooperation with the community, with the users. We call streaming with Stream Native. So if you are Lakehouse vendors, I would like to kind of figure out how to integrate together with you so we can stream the data into your Lakehouse. If you are a data processing engine, SQL query engine, we'd love to kind of partner with you. So to figure out and iterate on how the API look like, that people can use a data streaming system together with Lakehouse more. So that's the talk we're going to present today, and the talk is all about money, but it's also beyond money. And hope you enjoy the talk, and if you have any questions, there's time for questions.